Welcome to Lesson 9C, choked+Rayleigh flow. In this lesson, we'll discuss what happens along the Rayleigh curve when the rate of heat transfer changes, and we'll introduce and explain choked+Rayleigh flow and the sonic or critical conditions. We'll discuss the heat transfer limit when the Rayleigh flow is choked, and then finally I'll summarize which gas properties increase and which decrease in Rayleigh flow. Here's a summary of the equations that we've had so far: mass, momentum, energy, and then some thermodynamics equations and the ideal gas law. I want to concentrate now on what happens when we add too much heat. So let's consider Rayleigh flow with heat addition. We have our duct and our control volume inside going from 1 to 2, and heat is added. Again, either at one place or through a flame or distributed along the wall. This results in the Rayleigh curve, which I'll sketch here as a TS diagram, with the subsonic and supersonic branches, maximum entropy location, maximum temperature, etc. Recall that the Mach number is 1 at this maximum entropy, the rightmost location on the curve. If we start at some state 1, and add heat, so we have heat addition, state 2 will lie somewhere to the right of state 1, since entropy is increasing as we add heat, as we've discussed previously. So Mach number goes up on the subsonic branch, and temperature also goes up and then a little bit down, while Mach number continues to increase all the way to Mach number 1. If we add enough heat, Mach number goes to 1, and the flow is what we call choked. These conditions at Mach number 1 are sonic or critical conditions at sonic Mach number. In other words, if we get to this point, Mach number 2 is 1. We'll use an asterisk like we did previously with converging diverging ducts to indicate critical or sonic conditions. When M2 is 1, we have what we call choked+Rayleigh flow. We're dealing just with the subsonic branch in this case, but I'll also talk about the supersonic branch. If we start somewhere here, Mach number decreases from some m greater than 1 to m equal 1 in that case, and the flow still becomes choked. Now let's discuss in more detail choked+Rayleigh flow for the subsonic branch. Consider the case where location 2 is the exit plane of our duct. So here's our control volume, with 1 somewhere upstream and flow from left to right, and we're adding heat. This Mach number is M1, and downstream we have Mach number 2, which if the flow is choked is 1. And I note that we can also call this condition E, the exit plane of the duct. When the flow is choked, state 2, or state E, is the sonic or critical condition, so T2 is T star, M2 is 1, and other properties like stagnation temperature, pressure, etc. are all critical conditions or sonic conditions. And the heat transfer rate, Q dot, is Q dot max. This is the maximum possible heat transfer into this duct for this Rayleigh curve, noting that the Rayleigh curve itself depends on the conditions of the gas at location 1. So our energy equation is Q equal Q dot over M dot equals Cp T02 minus T01 in general. When choked, we get Q equal Cp T0 star minus T01, since T02 is T0 star. And this is Q max. Therefore, this is our choked+Rayleigh flow energy equation. And the caveat is that this is for a given upstream state 1. This Q max is the maximum possible Q for the given state 1. Well, the obvious question then is what happens if we keep increasing Q dot. Going back to our TS diagram, we keep adding heat until we reach choked conditions at maximum specific entropy, and Q equal Q max. If we keep adding heat, you might expect that we would start going to the supersonic branch, and Mach number would keep increasing above 1. But that's impossible because S would be decreasing, and when we add heat, S must always increase. So we cannot go supersonic when Q is greater than Q max. So what happens? It turns out that the upstream condition, or state 1, must change. In other words, this state moves somewhere else when we add too much heat. We then have a different Rayleigh curve. This whole curve will change such that our maximum Q dot will increase, and then we won't be violating the second law of thermodynamics. Now consider choked Rayleigh flow for the supersonic branch. We have the same setup with 1 somewhere upstream and 2 at the exit plane. But this time the flow is supersonic at state 1, and as we keep adding heat, M2 approaches 1 and is again choked when M2 equal 1, and we have sonic or critical conditions, which we use superscript star or asterisk to indicate. On our TS diagram, we're now on the supersonic branch, and as we add heat, Mach number decreases towards 1, and M2 goes to 1 when it's choked, again at S max. And this happens again when Q dot equal Q dot max. As you might suspect, we end up with the same energy equation as for the subsonic case, namely Q max is Cp T naught star minus T naught 1, and this occurs when the flow is choked. So we ask the same obvious question, namely what happens if Q dot is greater than Q dot max?
Dude, would the universe disintegrate into a giant black hole, man?
No, Joe, not exactly.
Well, more realistically, would maybe a normal shock form?
Yes, Jack, that's exactly what happens. Let's think about it. If we keep adding heat and the flow is choked, we can't go to the subsonic branch along this curve because S would be decreasing, and we'd be violating the second law of thermodynamics. But we can get to the subsonic curve if we have a shock. So for the supersonic case, a normal shock forms somewhere upstream of location or state 1. We then have subsonic flow, and we then have a different Rayleigh curve. We don't jump to some other location on this subsonic curve. Rather, we have a whole different Rayleigh curve with some new one somewhere here that has an entirely different Rayleigh curve. Let me sketch how that would work. We generate our supersonic flow with a converging diverging duct as previously discussed, and then this section of the duct is our Rayleigh flow region, and we'll let the exit plane be state 2. And state 1 is at the inlet of this frictionless constant area duct, where we add heat. In the limit, when Q dot is Q max, state 2 at the exit plane becomes the star or critical conditions, and if Q dot is bigger than Q dot max, a shock will form at the exit plane, and then that shock will move upstream very rapidly all the way back to 1 and then into the diverging portion of the duct. Across a normal shock, of course, the Mach number goes from supersonic to subsonic. So state 1 here, which was originally supersonic, now becomes a completely different state, which is now subsonic. Not only that, but we've changed the entropy and the total pressure, etc. across this shock. So state 1 is a completely different state with a completely different Rayleigh curve. And under these conditions, we end up with a new Q dot max that's greater than the original Q dot max, which allows us to add our extra heat. But the flow has completely changed because of this shock. And this one will eventually choke at a different Q dot max. And if we keep adding heat beyond that, the shock will move even farther. I'll finish up this lesson with a qualitative discussion of how gas properties change in Rayleigh flow. And let's talk about heat addition with a positive Q dot. Our energy equation is Q equals Cp T naught 2 minus T naught 1. And for Q positive, T naught must go up. What about total specific enthalpy? We know that H naught is H plus V squared over 2, which for an ideal gas is Cp T naught equals Cpt plus V squared over 2. So T naught is T plus V squared over 2 Cp. And since V is always positive, T naught must always go up. T naught goes up when Q is positive, and from here we see that T naught must go up since T is just a constant at T1 and V is always a positive number. So that's another way of showing that T naught must go up. And that's true whether the flow is subsonic or supersonic. What about the temperature itself? Well, again, sketching the Rayleigh curve. With heat addition, in other words Q being positive, temperature increases on both the subsonic and the supersonic branches, except for this strange zone or strange region where the temperature actually goes down. So T can go up or down as we keep adding heat on the subsonic branch. On the supersonic branch, T always goes up. But this strange zone is a very small portion of the Rayleigh curve. So we conclude that T goes up when Q is positive for supersonic flow, but T can go up or down when Q is positive for subsonic flow, but T goes down only in this little strange zone. What about some other variables like pressure? Our conservation of mass equation is ρ1 v1 equal ρ2 v2, which is a constant. I'll call it constant 1. And our momentum equation was P1 plus ρ1 v1 squared equal P2 plus ρ2 v2 squared, which is also a constant. I'll call it constant 2. I can rewrite this then as P1 plus ρ1 v1 v1 equal P2 plus ρ2 v2 v2 equal constant 2. But this is constant 1, and this is also constant 1 from our conservation of mass equation. So we can write this in general as P plus constant 1V equal constant 2 for any state 1 or 2 or anything in between, or P equal constant 2 minus constant 1 times V. And since these are both positive constants, we conclude that if the speed goes up, pressure goes down, and if V goes down, pressure goes up. And this is true whether subsonic or supersonic, just like our beloved Bernoulli equation. So that's how you can remember it. It also turns out that speed V follows Mach number m. In other words, as m goes up, V goes up, and as m goes down, V goes down. So on this subsonic branch, Mach number goes up, which means V goes up, and pressure P goes down. It's the opposite on the supersonic case. Mach number goes down, therefore V goes down from here, and pressure goes up. And we've already stated, and you can see on this diagram, that T also goes up until we reach the critical conditions. Whereas on the subsonic branch, T goes up, then T goes down in the strange zone. What about density? Well, mass conservation tells us that ρV equal constant, so qualitatively, density must go down as speed goes up, and vice versa. Let's do a qualitative summary for heat addition in Rayleigh flow. I'll do both the subsonic and the supersonic cases. And keep in mind we're talking about heat addition here. The properties that go up are speed, Mach number, specific entropy, stagnation temperature, and static temperature, but T does go down in the strange region. The properties that go down are density, pressure, and stagnation pressure. For the supersonic case, density goes up, pressure goes up, temperature goes up always, entropy goes up, and stagnation temperature goes up, but V goes down, Mach number goes down, and stagnation pressure goes down. Some of these are the same. S and T naught both go up, and P naught goes down, but many of these properties like P, M, V, and ρ behave oppositely between subsonic and supersonic cases. What about heat removal when Q dot is less than 0? I'll add here that H naught goes up in both the supersonic and subsonic cases for heat addition, but for heat removal, H naught goes down due to the cooling, and that's true in both the subsonic and supersonic cases. S also goes down for either case, but pretty much everything else is opposite. For example, V goes down, but P goes up. Mach number goes down for the subsonic case. And for the supersonic case, V goes up, M goes up, and P goes down. Temperature goes down in either case, but as we move to the left on the subsonic curve, T goes up briefly in the strange zone. I like to think qualitatively about which properties go up and which go down, and that helps us as we're analyzing flows to make sure our results make sense. Most of the problems we do will have heat addition, but the equations we develop can also be used for heat removal. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's what it's doing.